Hello, welcome. Before we jump into this, you'll need to grab your calculator so you can follow along. You'll need to grab Appendix 3, which states the Ka values for the weak acids. Alternatively, if you grab the OpenStax textbook online, you'll find Appendix H, which gives you the ionization constants for weak acids there. All right? Now, there are quite a few steps involved in this process. I'm going to take you through a sample problem here. And of course, I'll provide a description in the YouTube video with a link to just one other worked problem. But you might have to go through these steps quite a few times to gain mastery as a student, okay? So let's talk about weak acids. Weak acids are abbreviated as HA, and it turns out they actually react with water to produce hydronium ions. And it's the hydronium ions that are the business end of a weak acid and, of course, a strong acid, okay? So that's the characteristic defining feature. They produce vast amounts or a little bit more hydronium ion that's already present in water, okay? So HA is the weak acid and A minus is considered the conjugate base, all right? Now this equilibrium constant is usually very small. As you can see in your appendix, these numbers range from 10 to the minus 13 to 10 to the minus 2. Okay, so remember, if you have a very small Ka, it means that the left-hand side of the equation is highly favored, or it's reactant favored. So here's the equilibrium constant. Again, it's products over reactants. So remember, H2O is a liquid, so it does not enter into this chemical equilibrium. And the A just stands for acid. Technically, Ka is the acid dissociation constant, okay? So keep in mind, the higher the Ka, the more acidic. So 10 to the minus 2 is a stronger acid than 10 to the minus 5, all right? All right, so let me take you through some calculations here. So first, you want to write the equilibrium. You want to set up an icebox, and then you want to solve X for that equilibrium, and then you want to calculate the pH. So let me take you through these different steps here, okay? So in our example, what is the pH of 0.25 molar acetic acid? So acetic acid is, vinegar is an acetic acid solution, so this is typical of that. All right, so first you want to write out the chemical equilibrium. Okay, so acetic acid, you want to find out what that chemical formula is. Plus H2O. On the right-hand side, you write the conjugate bases, which are also in my Appendix 3. And then you want to write H3O plus. You need to memorize H3O plus, okay? All right, and then what you need to do is set up an ICE table. So I've got these chemical substances on the top, and I wrote initial, change, and equilibrium. And you want to start in the very top left corner of this process, and you want to write 0.25 there, okay? Now, water is a liquid, so just put a hyphen or an X. Probably not an X because that stands for the variable X, but just put a dash or something there, or just completely ignore it. We have in pure water 0 acetate, and in pure water we know from the KW or auto ionization we have minute amounts of H3O plus, but here let's just put 0, okay? And it's a good simplification, so just pretend like pure water has no H3O plus in it, okay? And compared to the vast concentration of acetic acid, it's not going to be an error, okay? So where do we put plus X? You put plus X under the zeros always, okay? So we're going to form products and we're going to consume reactants. And remember to add your columns to get the quantities on the equilibrium box, okay? So at equilibrium, we know 0.25 minus X is the concentration of the acetic acid, and X is the concentration of both acetate and hydronium ions, okay? Now, step 3 is to, once again, we have that written chemical equilibrium, is to write out the Ka expression, products over reactants. And remember, once again, H2O is a liquid. We don't stick it into this formula, okay? And now we substitute in the equilibrium values we just saw, X and X for the two products, and 0.25 minus X for the acetic acid, which is aqueous. The Ka value for acetic acid is listed in various tables, and in this appendix I have that I give my students the Ka, not sure if you can see that very well on the video, is 1.8 times 10 to the minus 5. So that's where you're going to find the Ka value, okay? If you are using OpenStax, you want to look at it alphabetically, and conveniently the first one listed here is acetic acid, so it's 1.8 times 10 to the minus 5 in the OpenStax textbook as well. I suppose you could use Google as well, but that's a little risky because you can get everything and everybody's opinion in the process. Next, what we want to do is make this very, very important simplification, okay? Now, because our equilibrium constants are very, very small, we assume that x is very, very, very small, which means that 0.25 minus x is about the same thing as 0.25, okay? So if on your calculator you did 0.25 and you subtracted 0.0000001, that's going to be about 0.25. So that's sort of like what we're doing here with the simplification, okay? So in the denominator, the bottom part of this fraction, 0.25 minus x, we just write 0.25. And this helps us avoid using the quadratic formula. Okay, this simplification will always be valid in my class. Check to at the end to verify that it does not introduce too much error, okay? All right, now what we do is we basically combine the x and the x to give us x squared, and we multiply both sides by 0.25 and follow along on your calculator to make sure you're getting the exact same thing. I am known to make mistakes in class, so I get 4.5 times 10 to the minus 6, but that's before I do the square root, so make sure you do the square root there, and I get 2.1 times 10 to the minus 3 on my calculator, okay? So what does that x mean? Well, you might have to go back to the ICE table and look. X stands for the hydronium ion here, okay? The hydronium ion. So now what we want to do is plug this into the pH equation, okay? pH is power of the hydronium ion, okay? That's literally what it stands for as proposed by the creator, and it's given this function here. It's minus log H3O plus. So make sure you use the log key on your calculator. I'm pointing to the one that can be found here on my calculator, but you just want to stick it in there. You have a negative sign there, okay? Log 2.1 times 10 to the minus 3. Punch that in on your calculator, and you will find that you have a value of positive 2.68. So that is the pH. Remember that if your pH is less than 7, it's going to be acidic, and so let's do a reality check. Is it less than 7? Yep, it's 3 or so, so that means it's less than 7. It's acidic. If your pH is above 7, we say it's basic or alkaline. If your pH is equal to 7 exactly, we say the substance is neutral, okay? Some buffers, and of course, pure water is neutral. Thanks for watching. Please check the description of the YouTube video for an additional problem. Please like this video if it helped you out in any way, and please consider subscribing. Have a great day, everybody.